All right, everybody, here we go. Unit 2.8, inverse functions. Emphasis on... All right, you get it. Anyway, this topic here does involve one of the ideas we talked about early in the year, some of the most misused and confused words that exist in all of math. This is one of them, inverse functions. Sometimes this is a topic that's taught in Algebra 1. Sometimes this is a topic that's taught in Algebra 2. Sometimes it's not. That's why it is covered in this AP course before you get to, or before we even dive into, exponential and logarithmic functions and the connection between them. Let's get started. All right, everybody, here we go. Inverse functions. Now, inverse, it's one of the three most misused and confused words in all of math. Remember, opposite, inverse, and reciprocal all mean different things. This entire section is focusing solely on the word inverse. One thing again to remember, opposite, inverse, and reciprocal all mean different things. All right, here we go. An inverse relation will undo any given relation. Every single inverse relation can be found by switching or flipping each x and y value. Some situations, the process is intuitive, but other times it may not be as obvious. We need to understand that inverses are a concept in math. One of the most important parts we're going to see down the road is how to show the notation for an inverse function. The difference between telling what an original function is and where its inverse sits will make the difference between domains and ranges down the road. Now, opposite means you just change one sign from positive to negative or negative to positive. A reciprocal means the denominator and the numerator get flipped. An inverse just means simply you switch your x and y's. So if I'm giving you this table as an x having 1, 3, 4, and 6 and y with negative 1 over here to 2, what would the inverse of that relation? Now, a relation is just a set or a group of ordered pairs. What would this table look like if this were the inverse? As we're going through these videos, feel free to hit pause to work out the problems yourself, or even along the way, or just to double check yourself after you try all the notes along with me. As we took this inverse table, notice all I did was I took all of my y values and I made them my x values. And I took all my original x values and I made them all my y values. And again, I have to give some sort of notation to show that this is my inverse location of ordered pairs. Now, the original table here is a function. Why? Because each x value has exactly one y value. Now, this inverse table, is this inverse representative of a function? And this is going to be the catch to some of the more trickier parts to working with inverses down the road. If the original function's a function, cool, the inverse is possible. But not every function that we start with is able to have an inverse being taken of it. Case in point here, this x has a value of 2, and this x also has a value of 2. Remember what the old definition of a function was? Your x values can't repeat, or every input value has to have one unique output value. We'll get more into this down the road, but as you create inverse functions, you just have to make sure you do all you can to show that they are still a function, even if some values in the domain, the new domain of this inverse, don't work. All right, so here we go. We saw a more basic example of using a table, and I'm still going to use a table here to prove or to show what the inverse of this function is. I'm going to pick key values. The key values I'm going to pick are the ordered pairs that have these nice little crosshair crossing points, namely here, 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 and here. And those ordered pairs, when I go through and label them, I'm going to create a table off to the side. And I'm going to have my original table sitting here, and I'm going to have my inverse table here. And once I have all my values plot for my original table of this function and this graph, I'm going to create my inverse table and then plot those on this graph to show what this new graph looks like as an inverse graph. And hopefully it still is a function. Now, we'll get more into the terminology here in a second, but this function here, this sketch here, yes, it is a function to start that we see in our notes, but I'm telling you now, the sketch or the inverse sketch that we're going to show is not representative of a function, and you'll see why in a second. Now, if we take a look here at this function table, from the values that I have of my original function here in red to my values that I have down here in blue, and I just flip my x and my y values, On the inverse here, every single x value is different. So I would say that this is a function. The inverse that we plot is a function. But if you go over here to this table here, or sorry, back to the graph, you'll see that the line in blue that I plotted out all the ordered pairs here is not representative of a function. Even though these points here show us that it probably is a function, plotting this here, and you'll see between 1 and 2, this blue line or this blue graph is not a function. It is still an inverse because all I did was flip my ordered pairs, but it is not a function. Now, there is a difference there depending on the question that's being asked of you. You might be asked just to find the inverse. Great. But you might be also asked to verify if it's a function or not. So here, even though it does not show that the ordered pair, the x values repeat, between 1 and 2, you can see it most certainly does not pass the vertical line test almost anywhere. In fact, it crosses it 3 places the entire time. Now, what makes graphs of inverses and their original functions even more unique and the most important part of them speaking graphically, there seems to be some symmetry here. There seems to be a reflection here. This part of the blue graph looks just like the original part here of the dots in red. Same thing goes, well, kind of, I guess, for this. But there is a symmetry here. And the symmetry that exists is true for all inverse functions. There is a reflection over, about, or across the line y equals x. So anytime you have one function and its inverse, whether or not the inverse is a function or not, it will reflect evenly over, about, across the line y equals x. My pen can work. There you go. Now, how do you know if you have a reflection over, about, or across the or the line y equals x? This ordered pair here from the inverse, if you drew a perpendicular or an altitude right to the line y equal to x, will be the exact same distance as here. Same goes for every other corresponding pair of ordered pairs. Now, let's take a look at how some of these inverse functions can be played out even further. After taking a look at what the graphic representations of inverse functions are, I'm notorious for saying numbers change, math doesn't. On the very first screen, all I said, or all we defined inverses as flipping your x and y's. Well, all of a sudden now you're asked to find the inverse for the function f of x equals 3x minus 7. Well, if an inverse is just flipping your ordered pair, x and y values prior to this, it should be the exact same thing here, because I'm still asking you to find the inverse of a function. Well, all of a sudden now I'm telling you that the steps to find, algebraically, one equation's inverse from the original function are just that you flip your x and y values and then get y by itself. That's it. Now, those are two simple sounding steps, but there are some pretty tricky steps of algebra along the way, depending on what the function is to start. Now remember, your original function should be a function. In this case, it most certainly is. It's just a linear equation with a slope of 3 and a y-intercept of -7. Now, we're going to go through and find out what the inverse of this function is algebraic. Once I went through and identified what my actual inverse function was after flipping my x's and y's and solving for y, I get y equals x plus 7 over 3. This is my inverse function. Now, to write this, it would actually be f of x equals x plus 7 over 3. Now, this notation is correct in the sense that this shows what my inverse function is. But for any function, I can't have an f of x equaling one thing and then an f of x equaling something completely different. So some certain notation needs to be shown here. The notation that's used for inverse functions is f to the negative first of x. And here's where some confusion usually starts to set in. This usually means a reciprocal notation. If I had x to the negative third, that would equal 1 over x to the third by the properties of exponents. This is why I think that opposite, inverse, and reciprocal terms get thrown around and mixed up and confused so often. So this f to the negative first is only notation. It has no true mathematical representation. We're not going to go through and take the inverse or reciprocal of anything. This is just the notation to show where the inverse is compared to the original function. Now, way back when we found domains of functions, that you had this denominator of 3, the only two restrictions in math, you can't have a value of a 0 in the denominator or a negative under a radical. Turns out that this domain is going to check out just fine, and in the end, this inverse is also a function. Now, there's a whole table down here to show what happens if you have multiple x's in a particular function. Notice the very first step, switch the x and y values. I left this in the notes because I think for some people to see these steps, knowing what to do for all the problems involving some factoring here, everyone's favorite topic. But in the end, it is just 2 simple steps. Switch your x and y's and get y by itself. Let's see what some more algebraically intensive problems look like from finding an original function and then finding its inverse. I'm going to leave this table here off to the side just for you to reference at any time. But the 2 questions that you're asked to find down here are to find the inverse functions for each of the following. These are rational functions. This denominator here of x plus 3 tells me that I cannot have a value of x equals negative 3. That will break my calculator. It'll make my calculator melt. It is not included in the domain. Every other value works, checks out, and is fine. Here, all of a sudden, x minus 3, cool. I know I have a value of positive 3 that doesn't work in the domain. Even though there are domain restrictions, meaning values that cannot work or will not work, it doesn't mean something's not a function, it just means you have to exclude those. I'm going to follow the same 2 steps I did on the previous screen. I'm going to go through and switch my x's and y's, and then get y by itself. Now, my inverse function here for this first function from f inverse of x, or the inverse of f of x, is negative 2 minus 3x over x minus 1. Here's the catch. In this step here, I decided to make it, when I subtracted 3x from both sides, I decided to make it negative 2 minus 3x. I could have made it negative 3x minus 2 and still have the same correct answer. Then dividing by x minus 1 still gives me x minus 1. The same can be said over here. When I got the 3x from the left side to the right side, I could have put 3x plus 1. Now, addition, obviously there's commutativity where order doesn't matter. 5 plus 7 is the same as 7 plus 5. But for subtraction, commutativity doesn't exist. There are alternate forms here of these answers that you can have if you have negatives kind of hanging around in front. Now, what you have to be conscious of when you're looking at the different versions or styles of the answers is what would happen if you had a negative in more places than where it currently sits. Now, if you take a look here, I factored out a negative from the numerator only, obviously, so I have negative 2 plus 3x with the negative sitting out in front. Now, since it's a negative, I can also put that negative in the denominator. Most of the time you shouldn't see that, but I could. So I get 2 plus 3x over negative x minus 1. And then if I distributed that negative to the bottom set of parentheses here, I'd get 2 plus 3x over negative x plus 1. All 4 of these are correct. Now, which version you may see as a multiple choice option or the math someone may present to you, I don't know. I have no idea, but these are 4 equivalent expressions for what this function can be. Notice, my domain here did not include negative 3. Now, can I have negative 3? Absolutely, I can. The value I cannot have is a positive 1 because of that domain restriction. Over here off to the side, I can't factor anything for the the inverse function for g, so I'm kind of stuck. I'm just going to let it be at 1 plus 3x over x minus 2 as my only realistic possible answer for that inverse. All right, here we go. Now we're going to start sketching inverse functions. Not necessarily just point plotting, but kind of just point plotting. The main idea here is that you're always going to have the reflection over about across the line y equals x. So you always want to know at least what that line y equal to x looks like. Any point that does cross on the original function on the line y equals x, those points are going to be coincided. They're going to be the exact same. I personally am a fan of just looking at key ordered pair values and trying to sketch it from there. Now, the other way to do this, as I said before, is if you had the line y equal to x and you drew points from one side of the original function across the line y equals x, the same distance in a perpendicular way, then you'll have the other inverse sketched. This is your standard parabola, shifted 2 units to the right, which I'm sure all of you understand that this equation would be g of x, f of x, a of x, whatever, y equals x minus 2, the whole quantity squared. So I'm going to sketch the function here by listing the ordered pairs or showing some of the ordered pairs, and then from there, sketching out and connecting the dots. All right, so take a look here. My original ordered pairs in blue, I plotted them out. Some of them got overlapped again. Notice the line y equals x. This point was blue underneath that red, and this point was blue underneath that red. Notice the red points also fall on the line y equals x. Now, if you take a look, when I switched my x's and my y's down here in this table, it created this red graph. I think it's easy to see how this original parabolic looking function is just turned on its side. So when I flip my x's and my y's of an original function, the inverse creates a graph of an inverse, and that is true. But take a look here. Does that graph in red actually create a function that's an inverse? I'm hoping the answer you thought of there was no, because it fails the vertical line test. There are ways to manipulate the original function in order to not have to change any of our algebra in order to create an inverse of a function. On the next screen, very briefly, I'll show you what it's like to restrict a domain of an original function in order to create, or when you do create, by the same exact steps of just flipping your x's and y's, when you create that inverse, it'll automatically be a function. Take a look here for the second graph of b. Now this is more of a repeating, maybe a cubic function, as from the left and from the right, it does take off and go toward positive and negative infinity. I'm going to plot some key values here in 2 tables up above, and then I'm going to sketch what I think the inverse graph would look like. Is it going to be a function? What do you think? Now, if you take a look here, my red dots, I only chose 3, and these should be red. You get the idea. Anyway, the graph does approach from here, peaks out right around like negative, sorry, 2 comma like negative, 2 comma negative 1-ish right about here, and then goes and repeats. Graphic design is my strength, you can tell here. Anyway, this is most certainly not a function. Is it an inverse? Yes. Can you restrict this domain of this original function in order to create the inverse that you have be a function? Of course. Let's take a look here real quick of not just how to flip x and y values, but how to restrict a domain. And I'm going to focus again on this specific example here of how we can cut stuff off of the original function in order to create an inverse function. So here we go. Here's that original function, that quadratic function that of f of x equals x minus 2, the whole thing squared. So if you take a look here, this is a function because it doesn't fail the vertical line test anywhere along its domain from left to right. Now, if I did, or when I did sketch this graph, remember it turned and it looked like this, so it failed the vertical line test every single time. What could I do to this original function in order to not have this thing fail the vertical line test? Well, what has to be eliminated from the inverse graph in order to have the vertical line test pass for the inverse function? Well, I need to not have a lower half or an upper half of this graph. So I, in my original graph, have to compare this upper half of my inverse to the original to see what it matches up with, and I have to compare this lower half of my inverse to see what it matches up to in the original function. Well, the easiest way for me to do this is to try to sketch out the line y equals x. Because remember, an inverse function has to be reflected over about across that line y equals x. So let me do that. So here we go. What I did was I put the 3 ordered pairs I'm going to focus mainly on here, and I drew the line y equal to x for my function that we see. Now, in this parabolic function, and most of the time when you have to restrict a domain, it's kind of visually a giveaway as to which value is the key value. This value of x equals 2 is my restriction value, or where the function changes from decreasing to increasing. So I'm going to look here at x equals 2 as a potential value for where I'm going to restrict my domain. That means this splits this graph into 2 halves. A left half that goes like this, and a right half that goes like this, and a left half that goes like this. Now, when I sketched my function for this inverse, I know that the graph looked like this. And what you see here is you have the option. When you restrict a domain, there's not necessarily just one way to restrict the domain or to cut values out. Let's just say in my domain here, in the original domain that I have, my original domain here is negative infinity to positive infinity. But what if I made my domain 2 to infinity? Meaning I'm only going to focus from here all the way out. Well, going back to my sketch, only 1/2 of this graph is the actual reflection to my right half here in red of this quadratic graph. Now I'm going to try to speak as slowly as I can, and feel free to review or rewind at any point. But I arbitrarily chose my domain to be 2 to infinity, meaning I'm looking at only the right half of this graph. Technically, this left half does not exist to me because I'm only focused on this right half. I arbitrarily picked that right half. So when I find the inverse, by sketching the ordered pairs that exist here or anywhere, which half of this graph here in blue am I going to have? Is it going to be the upper half that I focus on, or that will be produced from the inverse of the original red, or is it going to be this red or this lower half here in blue? What you have to remember is that every inverse is a reflection across the line y equal to x for its original setup. Well, if you take a look here, this top half is a reflection of what I have. So if I got rid of my lower half value of that inverse graph, then all of a sudden what I would have is I would have just this upper half of blue and this right side of red. So when I restricted the domain of this function, I picked 2 to infinity. I could have also picked negative infinity to positive 2. So all of a sudden now I'd be focusing my attention over here on this left side, which means the reflection or the half of the inverse graph that would be shown would no longer be this top half. It would be the bottom half here that I, for some reason, couldn't figure a way to use the eraser function, so I had to draw it with a white pen. Now, that idea of 2 being my restricted location value, where I'm going to pick the left side or the right side, is not an accident. The original function here is f of x equals x minus 2, the whole thing squared. Take a minute and think about figure out what the algebraic form of the inverse will be to x minus 2, the whole thing squared. Now, most of you probably went through and figured out that the inverse of this function, x minus 2, the whole thing squared, is the square root of x plus 2. Notice the plus 2 is not connected to the x, so it's a vertical shift of 2 units, or vertical translation of 2 units up for the square root function. The square root function originally looked something like this. You can see through here, and it moved up 2 units, so it's exactly what we have here. But what we just did not account for any domain restrictions. It was just pure algebra. So how did this function actually just tell us the square root of x plus 2, and how did it magically end up here? Well, there's a step, and it's the very first step to get rid of that squared. Now remember, this is our whole original function without a restricted domain, which means it's the entire graph here that you see in red. That's what we're finding the inverse of, because we're not restricting a domain for this last little example that I'm making up. Instead, we're just doing pure algebra to find out what the inverse is. Well, why did we only account for 1/2? How do you get rid of this squared term? You take the square root of both sides. And when you take the square root of both sides, technically, your answer is a plus or minus square root of x, or square root of whatever you're taking. Normally in math, we don't worry about the negative because it deals with distances or whatever the situation may call for. But if you think about positive square root of x plus 2, which is what this blue graph is, and then negative square root of x plus 2, which is what this other part of the blue graph is, this accounts for both the positive plus square root of x and the negative square root of x plus 2. So technically, this is what the inverse of this function would be. Now, if we're restricting domains, and I'm telling you from 2 to infinity, my inverse, you have to pick. Is it the positive square root of x plus 2, or is it the negative square root of x plus 2? Well, if I'm restricting my domain here, my inverse is square root of x plus 2 because that's the top half. If I'm restricting my domain here from negative infinity to positive 2, then all of a sudden my inverse of this function telling you what to restrict the domain to has to be the negative or the upside down square root of x. There's a lot of math going on this screen. It's almost 8 minutes for one problem. We'll talk more about restricting domains because I'm sure there'll be questions down the road. But for right now, feel free to hit pause, rewind, go back, and rewatch this slide just to see if it clicks even better the second time around. Because I like to live dangerously, I'm going to ignore everything that's going on up here, and I'm just going to skip right to the setup here. Let f of x and g of x be functions. Cool. Determine if they're inverses. All right, so step 1 here, it says find f of g of x. So it looks like I'm taking my original function and I'm substituting into it the actual function for g of x. Looks like I'm taking the second function g of x and subbing in the f of x over here. It looks crazier than what it's going to be, I promise you, but all we're doing is composing one function of the other. I'll be honest, I'm not usually a fan of showing this type of step or this setup of algebra because sometimes I've seen students make up math to know what the end result has to be. But take a look here. I composed f composed of g and g composed of f. What both happened here? What did they both reduce to? What did they equal in the end? They equal just x. Now, why is this x unique? Why is this x important? Do you remember way back when, a few slides ago, when I said if you have an inverse function and the original graph of it as well, that any points that are on the line y equal to x will be part of that inverse setup? This connects directly back to the line y equals x. So in order to show if two functions are inverses, the most algebraic and best way to do it, in my opinion, is to show that f of g of x and g of f of x both equal x in the end. If one of them equals x plus 2, stop working, go on to the next problem, because that means they can't be inverses. But whatever you do, please don't just make up math because you know that stuff has to happen along the way in order to get that to equal x. Next up, we're going to take a look here and still verify that the functions are inverses of one another. But notice here, the values of x that you have to be greater than or equal to 10. What if I plugged x equals 2 into a function? Well, that doesn't affect this all that much. But if I plug the 2 in here, what happens? My calculator melts. So this is the cutoff point for where this function starts to change from not working to working or working to not working. It doesn't affect the first function, but it most certainly affects the other. The good news here is that it really doesn't affect our algebra along the way because you're still going to compose h of k and k of h, and the same thing down here. X can equal 0 because you have a 0 as my restriction in this domain. X can equal 4 because I have a 4 as my restriction in this domain. I'm still going to do the pure math or the pure algebra, like I said, by subbing one or composing one function of the other. And in the end, hopefully, they are both inverses by saying they're equal to x and equal to x. Now, if you take a look here, all the math does check out. You get some funny using reciprocal values over here to cancel terms out. But in the end, they are both inverses of each other. One little catch here. When you take the square root here of this x squared, sometimes people ask, well, how come I don't have to worry about the plus or the minus here? Because I have a square root. We just got done talking about how when you have a square root, the positive and negatives have to be accounted for. There's a difference of having the square root already established in the problem versus taking the square root of both sides. Because the square root's already established here, I don't worry about the negative portion of this. There's another case involving absolute values and why I'm choosing to use the positive version of x, not the negative that could be hanging out here. But the long story short here is that if you take the square root of both sides, that's when the plus and minus needs to occur. Here, the square root's already established. We're done. All right, that takes care of the first part of these notes. Let's take a look at part 2's notes, and then I'll set you guys loose. All right, everybody, here you're going to see my age on full display and show you why I really go old school at some of my steps along the way. Long story short, you know how to find inverses. You just flip your x's and y's. The function notation here, if you have this inverse notation, this -1, it means nothing mathematically other than just showing you notation and keeping your functions organized. Well, there's a little bit more of an in-depth approach to looking at domains and ranges of inverse functions. The domain of f is the range of the inverse, and the range of f is the domain of the inverse, and that is blatantly clear if you're looking at tables and how we created tables in part 1 of the notes prior to this. But all of a sudden now, you're going to get into composite functions. And you're going to get into a new little step here that's going to be asked of you saying, let g be the inverse of f. So you're not going to see that -1 notation. But what you're going to know is that g is the inverse of f, so it's going to have the same properties, just with not the -1 notation. If you take a look here, I have my table of my x and my f of x. Well, that's my original. And then based off of all of these other values down here, I'm going to go through and find or create the table for the inverse function to this original function. Now, there might be some people here that can say, oh, here's my domain, here's my range. Anytime I'm asked a question down here, in my mind, I'll just flip the idea of domain and range. If that's you, please do that. It's not me. I need to physically go back through and see these tables that well, my pen didn't work so well here, but you get the idea. I need to see these tables of values. I need to use one form of the other. I'm not going to do all these problems. I will show you the answers that exist in the answer keys as well, but I'm going to pick a few of these problems. First, letter A, f of 0. Well, all of a sudden now this doesn't involve anything from my second table. Over here of my inverse. Let me label that. Inverse. Now, my function f of 0, so I know my input value is 0, my output's 1. So all of a sudden, this just turns into f of 1. And now I go to my table for my input value of 1. I get an output here of -1, and boom, I have that set up. But all of a sudden now, if I'm taking a look here, notice what changes. All of a sudden now I have my function g of -1, g of -1 inside or composed of the function of g. This is an inverse composed of an inverse. Take a look what's being thrown at you here. It's inverse notation, but I don't have anywhere at all on my tables an f of -1. So what does that f of -1 represent? Where do I pull this value? Well, I pull it from this function for g. So I'm going to pick letter E next to do. So my function value here at -2, well, my input value is -2. It means I have an output of 3. Hopefully in my table, I have an inverse value of x equals 3, and I do. If I didn't, not a big deal. It'd be undefined or no solution. But my output value here then is -2. Well, the negative is right there, I promise you. Anyway, take a look and try to figure out the rest of these problems here. But again, some of you can go through and figure out that the domain is the range and the range is the domain. That's excellent. I'm old school. I like to go through and just create more tables. All right, here we go. Now all of a sudden we're given a graph of a function, not necessarily just a table. That's fine. It's asking us for some very specific information. What's the minimum value, meaning the y-axis value here? What's the minimum value of the inverse and the original? I don't know what the inverse looks like. So because, again, I'm old school, I'm going to go through and try to figure out the best that I can what the original graph looks like compared to what the inverse graph looks like. So I'm going to pick some key values along the way. I'm going to write it over here in a table for the original, and I'm going to draw the inverse. I'm going to sketch out my values just because I need to see it a little bit clearer. So let me get started on that. All right, so let's take a look. It says, what's the minimum value of k of x? The minimum value of k of x, this original graph here, is a -3. It's the lowest possible value there. Now it says, or asks us, what's the minimum value of the inverse of k of x? Well, the lowest value I see here is -4. Now, could you have gone through and said, oh, well, if I take a look at where my lowest ordered pair is on the original function, this ordered pair here is -4, -3. So my lowest value here is a -3. For the inverse, I know it has to be -4 because that's my ordered pair, and I'm just flipping my x and my y's. Please think that way if you can, if you want to. Again, I like to see everything it takes a few extra seconds, but I like to see everything in table form wherever possible. Next, it asks us to find the inverse value of k of 6 and the inverse value of the inverse of 4. Well, my input value here of 6 is off the chart, but I know I have it over here, and believe it or not, that says 11 right there. So that's what I'm going to say is 11. And then my inverse of 4, I go to 6. Looks like that answer is definitely graphable. I didn't decide to graph this. I just kind of threw the graph off the page, as you can see. But in the end, my tables here are really helpful. And again, I only picked values that have nice crossing points. So all of a sudden here, the next example that you see, I'm not going to really work through it. But if you take a look here, again, all the answers are in the answer key sitting in the room. But if you take a look here, my line of y equal to x looks something like this. So these functions are going to cross almost perpendicular like to the original line y equals x, but the answers in the process are the exact same as the previous setup. All of a sudden here you get one of my favorite types of problems, a multiple representation problem where you have a table and you have a graph. I'm going to give a quick scan here. Here's G. I will have to create a table to find the inverse of G, and I will have to create a table to find the inverse of H. Not backbreaking stuff, but I'm going to go and create the inverse table here for H. And then from there, I'll answer one or two of the questions down here that you see for the notes. In the end, inverses are just flipping your x and your y values, no matter what type of representation you're given, equation, graph, or table.